Alright, so in this video we're going to talk about an old sort of topic here that you probably are familiar with, Pascal's triangle. And what we're going to do is, first of all, also learn what it is, how it relates to binomial coefficients, and then start making the connections, combinatorial connections to this. Alright, so Pascal's triangle, right, is not something you need a lot of sophisticated mathematics to do. What you do is you create numbers below by taking the sum of the top two entries. All right, so this one's a 2 because 1 plus 1 is 2. I'll explain these ones here in a minute where they're coming from. All right, 2 plus 1 is 3, and 1 plus 2 is 3, and 1. All right, what's not written here, it's pretty uncommon to write, is there are actually infinite numbers of zeros going off in both directions. Okay, and so what this does is this, not only is this sort of true, but it just strengthens or reminds you that these ones aren't just made up, they are also the sum of the above entries. So 1 plus 0 is 1 there. So really the first seed row is really this top row. Then all the other rows are created by taking sums of the above two entries. And of course it's in this sort of staggered pattern. So next to this one is also a 0. There's a 0 there. So 0 plus 0 is 0. Right, and so on. So you can make all these extra zeros if you choose to do it. If you had some sort of staggered graph paper, you could do this quite neatly. All right, so I'll make a couple more rows until I run out of space here. Or we can have zeros off to the side here. And I'll do one more. So 1, 6. Hopefully you guys can see this one here. There's 15, 20, oops. I saw that mistake before I did there. It's supposed to be a 5, right? 4 plus 1 is 5. 15, 5 plus 1 is 6, and 1 plus 0 is 1. Okay, and this table is an infinite table, or infinite triangle of numbers. All right, so one reason why this is taught as a useful tool is because it gives you coefficients in binomial expansions. So a good use of this is, say, this row. This row corresponds to if you wanted to cube a binomial. So for instance, if you had x plus y cubed, this would tell you how to work it out. This would tell you the coefficient of x cubed is 1. Then the next term here would be x squared. Sorry, let me make some space. X squared y, coefficient of that would be 3. 3xy squared, and 1y cubed. All right, in sort of a similar fashion, if you did 1 plus x cubed, the cube is really small, it's a 3 there. You have 1x cubed, 3x squared, 3x, and 1. And let me just, for the fun of it today, right next to the 0 there and put a 1 there so you can see the coefficients. Okay, so this is true also in these above terms up here. These two middle ones don't need it, really. I could put a 1 here for the y to the 1, and a 1 there on the x for x to the 1. And here you could read this as x cubed y to the 0. And you could read this as y cubed x to the 0. Just keeping track of the fact that the exponents add up to the sort of the master exponent here on the left. All right, and so you can use this tool to expand whatever power you want. You just have to go far enough down in the rows. Okay, so we've, in the previous videos, we kind of already realized there is, I went through a sort of a word counting argument of why binomial coefficients give you these, and of course the words are all starting to mix together, right? So n choose k is broadly binomial coefficient. But we can say of what? So I'm going to go ahead and just make the claim now, and we'll prove it. So it's the binomial coefficient of x to the k in 1 plus x to the n. Okay, so I'm using this second expansion here. If you wanted to express this sentence in the above, then you just have to pick one as sort of your primary variable and then one as your secondary variable, and that works. Okay. All right. So this right here, in its own funny format here, the content of sort of our next video, and this is referred to as the binomial theorem. The marker's getting squeaky, so sorry. All right, and we'll prove this theorem using two methods. The first one we'll do induction, and the second one we'll do a combinatorial style argument. And in that one, we'll re-invoke that sort of word counting argument instead of using complicated computations. All right, so in this one, I want to have just enough space on here to make a couple observations, two observations in particular that I want to work through as sort of preliminary to get to this goal here. And as first of all, certainly we want, let me get another color for contrast here. We want to sort of not just claim this mechanism in sort of this pictorial elementary way, like, and I think this is sort of like an elementary school way, right? Something you can just say, okay, do this process, and then this gives you this, and right, we want to actually connect all these dots here. So first of all, what we want to do is we want to know that these n choose k numbers, as we know them, right, with factorials, actually add together in this process, right? We need to know that's actually true. So for instance, certainly we know 6 plus 4 is 10, right? But that has another meaning, so I have just enough space here, so 6. Well, okay, so that's in the row of something to the 4th power row. Let me use this orange since it's a good contrast here. These are instructions how to expand 1 plus x to the 4th. And 6, that is the middle entry, so you do have to kind of think through which one that is. And it's not particularly tricky, but you can, if you start wrong, it's a little confusing. So this is actually, this here is 4 choose 0, this is 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Okay. Or you can read it backwards as 4 choose 4, 4 choose 3, 4 choose 2, 4 choose 1, and 4 choose 0. Okay, I'm going to write these on here after I said that out loud, but keep in mind it does make it messy. So I'm going to write them in the ascending order, but keep in mind you could go backwards too. It just depends on your preference, right? So 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Okay, so I'm just putting next to it what these numbers are supposed to be in terms of n choose k. All right, now this next row is the 5 choose something row. And so this would be 5 choose 0. This is 5 choose 1. 5 choose 2. 5 choose 3. 5 choose 4, and 5 choose 5. All right, so then we have to isolate the numbers we're interested in. So 4 choose 2, 4 choose 3, and 5 choose 3. All right, 6 plus 4 is 10. So we're claiming, as an example, 4 choose 2 plus 4 choose 3 equals 5 choose 3. All right, so as a theorem, we want to make sure this mechanism works on all of these entries. And that theorem actually just involves, well, we turn the 4's into n's, so n choose k. That's going to be from 4 choose 2. Now, if I want to go up 1, I have to do n choose k plus 1. And then if I want to match this, it looks like it's 3 and 3, so I should be choosing k plus 1 here. Oops. Before I make a parenthesis mark, and get the top entry in there, right? So k plus 1. All right, now instead of 4s, I have a 5, so that's n plus 1. All right, so before we can prove the binomial theorem, what we need to do is we need to prove that n choose k plus n choose k plus 1 is this. It's n plus 1 choose k plus 1. Is this something memorized? Well, not really. You can actually always just refigure it out in Pascal's triangle. Half the time I do that if I can't remember where all the plus 1s go. But what's important to recognize is this is sort of that mechanism that lets you move from row to row to row. So we're going to say, okay, binomial theorem seems to be true for this top row, and that seems to imply that it's true for the next row, right? And we need that mechanism to kind of get that inductive proof built. Okay, so in the next video, I'm going to prove that theorem. And if I have room on the board, I'm going to try to prove it two ways. One is the algebraic method, which is very familiar, just do some calculations. And then the other one will do a combinatorial method, which seems very different in style, but it can be quite powerful if you can't do the calculations. Okay, and this one we can't do calculations, so we'll do both methods. All right, so I'll see you in the next video.